It's also wonderful to be celebrating Oscar's birthday. So some of us were trying to figure out how long we'd known Oscar, actually. And there are certainly a few people here who've known him for longer than I have, but not very many, I think. Because in fact, certainly I met him certainly by October 1988, because Björn and Oscar and I all shared an office as PhD students of Nigel then. So it's quite a long time. Great. So today I'm going to talk about some constructions in symplectic and complex symplectic and hyperkahler geometry that I've been interested in. There are quite a few authors involved in some of these constructions. The sort of stuff I'm going to particularly mention is kind of a progress report on some work in progress with Francis Kirwan and Johan Martins, but there are lots of other people like Andrew Swan who've been involved in some earlier stages. Some of the things I describe here. So I'm going to be talking about a couple of constructions, implosion and contraction, that have come up in symplectic geometry, but also have some kind of hyperkahler analog or partial analog. And I think the theme that I want to particularly talk about is I want to propagandize a bit for some ideas coming from physics, which I think are very, very nice. The idea of the more Tachikawa category. So I'm not too clued up on the physics, but I just want to sort of explain. I think it's a really nice formalism, a really nice organizing principle for some of these constructions that we're coming at from a purely geometric viewpoint. So that will be perhaps the central theme of the talk. So to begin, let me recall the construction of symplectic implosion. So this is just real symplectic geometry. So this now has been around for a while. It was Victor Gilliman, Lisa Jeffrey, Ray Samar, who wrote the original paper on this. I guess almost 20 years ago, actually. And the idea is, I don't want to get into all the details about this, but it's an Abelianization construction. If we have a symplectic manifold with a symplectic or Hamiltonian action of a compact Lie group K, then we can form a new space called the imploded space, which in a kind of canonical way, which has an action of the maximal torus. And these two are related in various ways that I don't want to get into because they're not so relevant for the rest of the talk. The key idea here, which is going to be very relevant to the more Tachikawa picture, once we've figured out this construction for the symplectic manifold, the cotangent on of K, then we can do it for everything. So that is the relevance, which I'm going to come to in a few minutes, to more Tachikawa. So this, in a sense, is a sort of universal example. So what do we actually do? How do we implode this thing? T star K, one of the sort of ways of thinking about implosion, and the way which I think is sort of perhaps generalizes best of a hyperkahler case, is a sort of master space in that symplectic reduction by the Abelian group at the various levels gives the co-adjoint orbits for K, which are the homogeneous symplectic spaces for K. So that's the sort of way of thinking about the implosion, which I think generalizes most naturally to the hyperkahler space. How is this constructed? Well, there are two ways to construct it, which is in the paper by these three authors. So we'll talk about how to construct this, the universal example, and then I'll say how that enables you to implode an arbitrary space. So one way is symplectic. So we take the subset of T star K, which is the subset of K cross the dual of the Lie algebra, which is the closed Weyl chamber. This, of course, is manifold with boundary. So this has got lots of faces, of course, and we collapse faces sigma by the commutator of the K stabilizer of sigma. So I should have mentioned, actually, a lot of the ideas in this talk are pretty closely connected with the ones that Jacques spoke about yesterday. His focus was more on the group-valued implosion, which is a story I won't want to get into, but you'll see a lot of overlapping ideas with what Jacques spoke about. So in particular, in the interior, there's no collapsing because the stabilizer is abelian. Okay. The collapsing occurs on the lower faces. Over here, do collapse. And then the origin, of course, at least if the group's semi-simple, which we're always going to be taking, full collapse. So it's not obvious, of course, that this does give you a symplectic space, but Gillam and Jeffrey Samar showed this does work, and it's not too difficult actually from that description to see that this is going to have the desired property. It's going to be a master space for the coadjoint orbits with the abelian reductions at the various levels. That's one way of thinking about it. For our purposes, there's another way, which is rather more relevant, perhaps. So, of course, it's kind of a common theme in symplectic geometry, but there's very often a symplectic, and there's an algebraic way of looking at things. This is a very common thing, and this is the case here. So, what's the algebraic viewpoint? This is an interesting object, and this is why Francis got interested in this, of course. This is very much her game. It is a non-reductive GIT quotient. It is a GIT quotient by the maximal unipotent group inside KC, which of course is not reductive. Okay. So, of course, for reductive quotients, that's the classical theory due to Mumford. The reductive quotient of an affine variety would be the affine variety whose coordinate ring is the group invariant elements of the coordinate ring of the original variety. That always works because it's a classical theorem, I guess, that ring of invariance is always finitely generated. If the group is non-reductive, of course, that can fail. So this doesn't actually have to exist as a variety in general, but it's a theorem. But in this case, it does exist as a variety. We do finite generation. Okay. So we have these two ways of looking at things. So perhaps let me mention an example, a simple example, although it's a slightly misleading one, a slightly atypical one. Yeah, perhaps it would be. Board management here. Okay, obviously, let's think of the simplest example, SU2. So what's going on here? From this point of view, we take top stratum is SU2 across the open bar chamber, the interior. And in this case, we only have one more stratum, which would be SU2 cross point. But then, of course, we're collapsing SU2, or at that green spot, equals the point. So the top stratum is C2 minus the origin. The bottom stratum is the origin. So what we get is C2. Okay. We could also see it from this point of view. Because what are we doing? We're looking at the action of N maximum unipotent on SL2C, and then what are the invariants? The ring of invariants is freely generated by the elements of the two columns. So again, we're getting C2. Okay. So that is a little misleading, because in the higher rank cases, actually the strata don't fit together to give you a smooth space. In general, in higher rank, we're always getting a singular space. So the SU2 case is a little bit atypical in that respect. So something to take away from this is we can think about this, and this is actually quite a nice way of thinking about implosions. This is sort of an affine completion of the top stratum C2 minus the origin. Okay. Now the general picture algebraically, the universal implosion, this non-reductive quotient, is a union of strata where the strata are indexed by the standard parabolics, and each stratum looks like that. It's the group modulo the commutator of the parabolic. So of course the top stratum is just KC mod n. So this is an affine completion of KC mod n.
Sorry, what is the relation between the parabolics and the non-reductive group here?
Yes, so these are the parabolics in KC, I should say. So in G equal KC. So the top stratum is when P is the Borel, and we're getting that.
And N was
N is the maximal unipotent.
Oh, maximum.
Yeah, yeah. So the top stratum is KC modulo N, the naive quotient, which is not an affine variety. The GIT quotient, which is an affine variety, is the affine completion we get by sticking in these extra strata corresponding to the higher parabolics. So perhaps a comment, we can relate these two pictures. Top stratum KC mod n, well, by the Iwasawa decomposition, we could factor KC as KAN modulo n. So we're getting KA, which is exactly top stratum here, K cross the open bar chamber. So we have this very, very nice picture developed by Gillam and Jeffrey Samar. We have a symplectic viewpoint and an algebraic viewpoint. So that's the universal implosion, the one that is this master space. How do you implode things in general? Well, let me just write down the formula. And then we'll see later the significance of this. Here. So if you've got a space with a Hamiltonian K action, what do we do we cross it with our master space with T star K implosion. Now, of course, T star K has two commuting K actions. We've imploded one of them to get in this construction that I've just outlined, say the right one. So this has a K cross T action. We've imploded one of those actions down to an abelian action. But of course, the great thing about this space is we've still retained the left action. The left action has survived. So we can now do the obvious thing. Yeah, bad, unpleasant notation here. That's now the symplectic quotient. This is symplectic reduction by the diagonal K. And that now is the implosion of T because it's the action is now survived. So that's the sense, as I say, in which this guy is a universal example for this type of symplectic construction. Once we can implode T star K, by that formula, we can implode everything. And I don't want to get into this, but the M implosion and M are related in all sorts of very nice ways, which make precise the sense in which this is a general abelianization. Okay, that's the symplectic story. Now, of course, if we have a symplectic construction, then obviously those of us from a certain geometric school will always want to try and find a hyperkahler or at least holomorphic symplectic version of this. This is a very common strategy, of course. Hyperkahler version. Well, we want to replace T star K by T star KC now. And of course, it's a non-trivial result, the theorem of Kronheimer, but this is hyperkahler. And it has a hyperkahler K cross K action, or if you like, it has and the complexification amount, of course, preserves the holomorphic symplectic structure. The symplectic implosion was that, the GIT quotient of Kc by n. The natural thing to do is to guess that the hyperkahler analog should be the holomorphic symplectic quotient in the GIT sense of this by n. So provisionally, we will form the holomorphic symplectic quotient of this by n in the GIT sense. So, well, the moment map is basically projection onto the dual of the Lie algebra factor. So we're basically looking at that. Or if we wanted to, we could identify on choosing an invariant in a product, we could, by linear form, we could identify n0 with B. So the hyperkahler version of the universal implosion should be that guy. And that actually does work. So in the AN case, the SUN case, paper by Francis and Andrew and myself, there's actually a quiver description for this stratified hyperkahler space with K to cross T action, complexifying to KC cross TC, because essentially we've kept the left action, but we've broken the right action down to B modulo n, the Borel modulo n, which is a torus action. So in general, by work of Ginsberg and Risch, this non-reductive quotient will exist, at least as some kind of singular holomorphic symplectic space. The actual hyperkahler structure is still a bit mysterious, but at least it will exist as some kind of typically singular variety with, at least in this stratified sense, a holomorphic symplectic structure. So there's a lot of things one can do with this. Gillam and Jeffrey Samar showed with a very natural, sort of using some representation theory, embedding of their implosion in an affine space, and from that you can see there's a toric variety sitting inside it. Ginsburg and Kazdan recently showed there's a similar, one can similarly define an embedding in the general case for this variety, and Francis and Johan and I think we can get a general description of a hypertoric sitting inside that. In the AN case, we knew that already from the concrete quiver description, but we think there's a general argument to do that. But what I want to concentrate on in this talk is the relevance to, let's say, more Tachikawa. And the key point is this formula here from the T star K example, how we get the general example. So this is something that comes from physics. So I should say there are some things about their definition that are not yet fully precise. In fact, there's an interesting project there exactly to completely nail down some things that the physicists glossed over a bit. But I'm just going to sort of give the general idea of the formulas in here. So what's their category? The objects are complex, well, in their case, semi-simple groups, but I want to consider, think of it more general, complex reductive groups. Okay. So those are two of our objects, complex and simple reductive groups. Now, what's a morphism? This is where things get interesting. A morphism is supposed to be a holomorphic symplectic variety, possibly singular. The exact nature of a singularity is something that has not yet been fully worked out, with E cross H action. There is a little bit of auxiliary data. There's also supposed to be, this comes from the physics, a circle action that a rotating circle action that scales the holomorphic symplectic form. That's not so relevant for purposes. So how do we compose morphisms? Well, actually, we just do the natural thing. J. So what have we got? We've got some. So we've got X. E cross J. That's got an H cross J action. So what do? Well, we start with X cross Y. Okay. And that, of course, now has that action. So then we do the obvious thing. We just symplectically reduce, holomorphic symplectically reduced by the diagonal. Now we get something. Cross J action, and that is our morphism. Okay, so back to the formula. Now, of course, this was in the case of compact groups, but obviously that doesn't affect the formulas. I mean, it may not be a sensible thing to do physically, it doesn't affect the formulas. And that is exactly what you're doing with implosion. So just forget for the time being that we're thinking of complex groups. What have we got? That's your M. Universal implosion is sort of a canonically defined morphism from K to C in that picture, because I say we've imploded the right action and broken it down to T action. And then you've got that. So the Goleman-Jeffrey-Samar procedure for imploding a general space, once you've got your universal implosion, is exactly composition in the real version of hyperkahler. A couple of other remarks. Runheim space T star G, where G is the complex reductive group of complexification of K, will add, of course, has a G cross G action, complex symplectic. That's the identity morphism in this picture. I don't want to get too into this, and I probably wouldn't have time to anyway, but so the idea is that the physical origin of this is that the physics should provide a functor from the Buddhism category of surfaces with boundary into more Tachikawa. So yeah, I don't want to say too much about that, but we'll probably get the idea that the cylinder is supposed to be mapped to that guy, which is a morphism from G to G, etc. That guy is supposed to be mapped to G cross the Slodovy slice with the hyperkahler structure of Roger Banowski, etc. So physically, what is such a functor is you choose a group, and then for each thing here, Riemann surface with punctures, you have a certain theory defined, and you take the Higgs branch of that theory, and that's supposed to be the symplectic thing here. So yeah, that's something I only want to mention. Another point I should probably mention is I've always been quite careful here to say complex symplectic rather than hyperkahler. Now, in most cases, of course, there is actually an underlying hyperkahler structure, which is much richer and much harder to, much more non-trivial than the complex symplectic structure. You can do that. The Moore-Tachikawa picture is not quite so nice for hyperkahler. And the reason is essentially actually quite interesting, that this guy is basically, how did Peter show that this was a hyperkahler structure? He identified this as the space of Lie K valued norm data on, say, an interval, smooth on the interval, moduli space of solutions to Norm's equations valued in Lie K, smooth on an interval. Now, if you think of these spaces not just as holomorphic symplectic, but as hyperkahler, this is not quite an identity, because the metric is getting shifted essentially by a factor depending on the length of the interval. So in some sense, you would get an identity in the A tends to 0 limit. So there are probably ways around that. It's been something my former student, Maxence Merons, has been quite interested in. There are probably ways around that by enriching the objects to include some extra data. But there is an issue there. If you want to make this picture work completely in the hyperkahler case, then there is some work to do then. Okay. So that, I think, is a very nice sort of formalism for viewing what's going on in implosion. I think this is very, very, very nice when I first heard about the Moore-Tachikawa picture. It's exactly what what Victor and Lisa and Rhea were doing, except in the real context. So let me conclude with the sort of development of this theme, which is what Francis and Johan and I have been thinking about recently. I should say, of course, I mean, to think of implosion in this picture, you obviously do want to enlarge that to be reductive rather than semi-simple. That may not be such a physically sensible thing to do, but just from the point of view of the formalism, obviously that's I think we'll rub this off. So that does actually raise an interesting point. If we do allow ourselves a little bit more flexibility than what Moore and Tachikawa did and allow reductive and semi-simple groups. Because what did we do? Let's go back to the formula for composing morphisms. We took these two morphisms, which are complex symplectic manifold to the appropriate group action. We took the product, and then we diagonally reduced by the H. Now, in general, of course, the J would survive, but nothing else would survive. But if the H were abelian, we pick up something more, then the other copy of H survives. So in particular, if it's, say, were equal to the maximal torus of C, let's think about dimensions. So the dimension of the implosion is that. That makes sense, of course, because I didn't leave the analog of the symplectic implosion being the master space for the coadjoint orbits is that this guy should be the master space such that toral reduction gives you the constant variety. So at level 0, it's an orbitant cone and so on, which have dimension in KC minus rank KC. So what would be going on here in our particular picture? We would be taking the right implosion here, I guess, probably the other way around, and the left implosion there. And then we would be forming the product. So the product would be product of two copies of implosion, the right implosion and the left implosion, by the diagonal. So what would we be doing? We'd be taking two lots of that dimension, and then we'd be subtracting off twice for rank because we're holomorphically symplectically reducing by TC. So we would get this object, which is the contraction of the same dimension as T star cross KC. But now we've picked up an extra toral action. So we're getting the same, if we apply this construction to the right and the left implosions, we'd be getting a new space of the same dimension as T star KC, but now with an extra action. We'd have the left and right KC actions, but we'd also have a TC action. So this is something that is known in real symplectic geometry. This construction would give you a symplectic contraction of this is due to Hilgert, Manon, and my collaborator, Martins. So we should think about this as a degeneration of T star Kc. And again, this is very reminiscent of what was in Jacques' talk. It's a way of degenerating T star Kc so that in the singular limit, you're picking up an extra abelian action. And that fits into some purely algebraic constructions by people like Ginsburg. So e.g., so again, thinking in the oh, I'm sorry, of course, we're in the real symplectic case now. In that case, that would be just a T degeneration of T star K, which of course could be thought of as G, which is Kc. So if K is SU2, then the symplectic contraction is, well, basically it's because this is supposed to be degeneration of T star SU2, which is SL2C. But SL2C, of course, that's xy minus ZW equal 1. But obviously, of course, you could replace the 1 by any other scalar. So if a scalar is non-zero, you're getting a nice smooth object. But if a scalar is 0, then it's degenerated. So that's actually a paradigm of a general picture here, that they can view their symplectic contraction more algebraically as a way of defining a family, degenerating a family that degenerates a group. And you see now, of course, in the limit, we've picked up an extra abelian action because we can scale the variables now, which you couldn't if there was an n0 thing. Okay, so this is this is interesting, and this is very much work in progress. For the T, yes, I mean here I think it simply would just be a simple scaling of the variables, which we only get when it's 0 on the right-hand side, but not, of course, for all the other members of the family that have a non-zero scalar there. So this is an example. I think it's the Winberg monoid construction, but of course, if we replace that by lambda and vary lambda, we're just getting 2 by 2 complex matrices, but that can be viewed as a degenerating family that degenerates for generic SL2C to the singular thing. So symplectic case, this is all very nice. You have this contraction construction. You can show that the original space will surject onto the contracted space. And using the hyperkahler formalism, once you've figured out the contraction for T star K, you can figure out the contraction for any Hamiltonian K manifold. The hyperkahler picture, or the holomorphic symplectic picture, is a bit less clear at the moment. It might be rather more messy. This is something we're trying to understand at the moment. So I think that actually may be quite a good place to stop. As I say, it's very much work in progress, but I think I really would propagandize for this idea from physics, I think, which gives you an extremely nice formalism for viewing some of these constructions, not just in the original context where the groups are complex semi-simple groups, but more generally, if the groups are just real groups, or if they're complex reductive groups. But both the implosion construction fits extremely nicely into their picture, and the contraction construction, which is quite well understood in the real symplectic case, but not yet well understood in the holomorphic symplectic case, also fits into this. And yeah, who knows, perhaps some of the physical ideas which generated the more Tetracolor picture, perhaps some of those will actually turn out to be useful in understanding the hyperkahler geometry of these things. Good, I think that's a good place to stop.
Are there some questions or comments?
Well, I have two questions actually. One is in relation to your last comment on that being the Wingberg monoid.
Right.
And so the Wingberg monoid construction can be generalized to actually a symmetric space. So if you have a group with an involution, right? I wonder if this story somehow has a version that is.
Yeah, that's a very good question, actually. I mean, if that's if the Wingberg formalism works there, you'd expect probably yes. I mean, one point that does occur to me, I didn't mention it in the talk, but what I've described in a sense is the simplest case of implosion. There are also partial implosions where, I mean, essentially, instead of taking the non-reductive quotient by the maximum unipotent, we're doing it by the unipotent radical of a parabolic. So certainly in the case of symplectic implosion, that does work. Now, it's still a conjecture whether these quotients make sense as varieties in the hyperkahler case, so that there are actually some physical reasons for thinking that should work, because in fact, I and my collaborators recently constructed spaces which look like they should be the symplectic duals of the partial hyperkahler implosion, actually, so there's some indirect evidence. So that might fit in with that story. But yes, I didn't talk about partial implosions, that would kind of fog the issue, but quite a lot of things one can do generalize to the partial implosion case, where we've now chosen a parabolic rather than working with the Borel and the maximum unipotent. So that might well fit into what you were asking.
My second question or comment is more speculative, is that in gauge theory, all this symplectic reduction and quotient, GIT and so on, very important, as you know. I was just wondering if there is a gauge theoretic situation where you have seen the implosion phenomenon, because there are situations in gauge theory where actually you are quotienting by a non-reductive sort of gauge group. And so
that's a good question. The situation is not fully satisfactory. There is a gauge theoretic way, which actually Francis and I and my former student Marcus Rosa wrote a paper on, of producing a space using NARM data on half-line, which has some similar properties in the sense that it has a stratified hyperkahler metric. There's a T action, and then when you reduce by the T, that actually fixes your stratum. So you now have a genuine hyperkahler quotient, and that will actually give you the constant varieties. Unfortunately, that's not quite the same as the algebra as a non-reductive quotient. So I think the answer would be that space, it's not going to be an affine variety. So there is a gauge theoretic approach to the subject, but it doesn't fully mesh with the algebraic theory. But I agree, it would be that would certainly be something we would like to do, is to have a gauge theoretic approach which is a better fit. It's somehow a little bit related. I mean, again, it's sort of the problem about the length of the interval again comes up, but somehow the co-adjoint orbits, or the constant varieties with the NARM data on an infinite ray on a half-line. The Kronheimer space is always viewed as NARM data on a finite interval, and so somehow that's the slight mismatch there. That's a bit of a problem. So again, as in a slightly different context, the length of the, in a sense, to make more Tetracolor work, you'd like to take the length of the interval to 0. But from the point of view of the implosion, you probably want to take it to infinity in some sense. So it's still a little bit mysterious, actually, what the correct gauge theoretic approach is.
Some more comments? Yes.
So in the physics or the algebraic literature, they attach a vertex algebra in this Moore-Tochikawa theory to the symplectic, holomorphic symplectic variety. Do you see any relationship to what you're doing with the vertex algebra?
That's not something that we've looked at. No, it's a great idea. That's not a direction we've gone down at the moment. But yeah, definitely something should be looked at. Yeah.
Because they don't know about the geometry. I asked the same question to them about do they ever see the hyperkahler metric, for example.
Sorry, you any joy in using quasi-Hamiltonian?
All right, good question. Yeah, in the implosion, the case of implosion. Oh, sorry.
Okay, sorry. Any joy
Sure.
in using in the quasi-Hamiltonian
Yes.
setup for this?
Yes, in the implosion, you can, well, certainly in the AN case where we have a quiver description of the hyperkahler implosion, there is a group valued analog of that just replacing doing the obvious way. You're getting multiplicative rather than additive quivers. Now, of course, you sort of kind of lose the hyperkahler geometry there. I don't think anyone's sort of figured out the hyperkahler analog group valued stuff, but certainly complex symplectically you can say a lot. So a certain amount of that does carry over. We haven't thought about how that might go with the contraction construction, but yes, implosion, there is to some extent, there is a group value analog of this, yes.
Probably an irrelevant and stupid idea, but you get away from the semi-infinite interval.
Oh, okay.
With the
that actually might be useful then.
So,
thank you.
Okay, some more questions? Well, if not, let's thank the speaker again.